in this few sections, we'll be reading about the microscopes, that is the different type of microscope. Before I go deep into the chapters, I wanted you all to remember the three important terminology: magnification, resolution, and numerical aperture. Now, why do we use a microscope? As everyone knows that there are minute particles which cannot be seen through our naked eye, and they can be observed only through the microscope. And what is the importance of that microscope is its magnification. So the organism is very small, which is not possible for you to see it through your eye. But when you are placing into the microscope, you can visualize the entire morphology of this organisms. So this enlargement is known as magnification. That is, the object or the specimen what you have kept under the microscope is still the same size. That is, the physical size is not changed, but only we are enlarging it, and this process is known as magnification. Then what about resolution? As you can read, that resolution is the finenesses, sharpnesses, and clarity of the produced image when viewed through an optical instrument. Optical instrument means here we are talking about the microscope. So let me explain it with two simple points here. You can see that here and here I have kept 2 points. But how does this appear to you? It appears to be a single point. There is no distinguish between these 2 points or the object. But these 2 objects which is appearing as a single object are 2 different entity or 2 different objects, that they are so close to each other that it is appearing to us as a single object. So in microscope, we can resolve these 2 points. That is, we can resolve the single point which we are seeing into 2. So resolution is the finenesses, sharpnesses, and clarity of the produced image when viewed through an optical instrument. So when I view this point in this optical instrument or in your microscope, it will clearly show that these are 2 different specimens or objective which were appearing to be as a single object. So we have resolutions in a microscope which will exactly focus, telling that the finenesses and the sharpnesses and the clarity of the object we are viewing. And the another important point is the numerical aperture. Now, this numerical aperture is critical because it limits both resolution and brightnesses of your image in the light microscope. So we define resolution as the distance by which 2 objects must be separated in order to distinguish them as a separate from one another. And if this doesn't happen, that means to tell that your numerical aperture is actually, if it interferes with the resolution, then what happens? It is limiting your resolution, and also it is limiting the image brightnesses, which should not happen. So what is the solution for this? So there is a definite solution which is given by a scientist, Rayleigh criterion, which is known as. So this is the formula. Here you can see that D is the distance. This distance is equal to a constant 0.61 times the wavelength of light that is generating the image divided by the lens called the numerical aperture. In short, they are written as NA. So this is your definition for your numerical aperture. That is the resolution limit. What is the limit of your resolution for a particular object? So take any objective lens, okay? You can see that there will be what is written as, for example, here it is 60x. 60x is what? It is your magnification. That is the how much it can enlarge. And then there is a slash and it is given as 1.40. This 1.40 is your numerical aperture, which is given by the Rayleigh constant. That is this. Okay. So the numerical aperture is equal to the sine theta. Okay. I'm not written here. It is equal to the sine theta. I think, oh yeah, here it is. So the sine theta, where this theta here, this one, is equal to the maximum angle of acceptance. What do you mean by this maximum angle of acceptance? That is, if you think about the light coming from your sample, the theta is the maximum angle of light that the objective lens can collect. Okay, and this is known as the refractive index of the media, that is between your specimen and the lens. I shall explain it again. So this numerical aperture we told is equal to the sine theta. So what does this theta means? Theta means it is the maximum angle of acceptance of light. Now you can see here, see the light is falling on your specimen, okay? On the specimen, what you have placed? You have placed the cover slip. And how are you visualizing your specimen? I'm visualizing through my objective lens. And between this lens and cover slip is what? There is a space or there is a vacuum, which I mentioned it as a media. And this lens, whatever the light is being projected from here, it enters into the lens. Okay. So how much light is taken up by your lens, how much capacity it can take up is known as the sine theta. So theta is the maximum angle of the light that the objective lens can collect. It is the refractive index. See, the light, it is refracting when it comes to the cover slip and then it is going this way. Okay, this is the refractive index of the media between your lens and the specimen. And this is the media or the vacuum. Now, we all agree that lens is not going to able to collect the 90-degree angle of light coming from your specimen. Okay. So the sine of 90 degree is 1. We take the sine, okay, of 90 degree as 1. Look at this. This is the light, okay, and this is the numerical aperture, and this is how the light is going. See, if the light is going in this way from the cover slip, if it is going in this way, in this direction, okay, it is not going to take up those light. It just gets refracted. So actually the light is passing in this way, okay, and this sine, whatever we have mentioned, it is considered to be as 1. So let me repeat it again. The lens is not going to be able to collect the 90-degree angle of light coming from your specimen. So the sine of 90 degree is considered as 1. So 1, the refractive index of air in a vacuum. So what is this 1? Of course, it is the sine we told, but from where did you get this 1? We have considered it from the refractive index of the air in a vacuum, and this one is slightly more in the rooms. Okay, so always when we are considering the numerical aperture, okay, your sine theta will be always equal to more than 1. Okay, this one is what? It is the refractive index of the vacuum or the room. When you compare it with the room or the vacuum, actually the refractive index is always more than 1. And that is why here you can see that your refractive index or the numerical aperture is always more than 1. So these 2 points are very important, your magnification and your numerical aperture. Because of this numerical aperture, what happens is that you can visualize the magnification, that is the enlargement, and the brightnesses in a better way in your microscope. Otherwise, it is not possible. So this is theoretically, they have produced it and they have constructed the microscope in this format. So when you compare all these magnifications or the objective lens, okay, usually we see that the oil immersion is the best one, okay, because it has a numerical aperture like 1.5. So again, the numerical aperture is the maximum angle of the light coming from your sample, I told, okay. From your sample that reaches your lens, and the lens collect the light traveling at an angle through the cover slip. So when we consider the different type of objectives, we know that the oil immersion is the best one, because what we are adding here, we are adding the oil, okay, so between your cover slips. Whereas the dry objective image quality will actually get worse. So it is better for you to always use immersion oil with an oil immersion objective, since the maximum angle of light that is collected by the lens, okay, that is collected by your lens increases with the numerical aperture. That means higher inner lens are going, okay, that the lights are going into the lens are collected more from your sample, and obviously this gives a brighter images. So when you are using oil immersion, you are using the oil in the oil immersion lens, and here what happens is your lens is able to collect more of the light which is being coming from your specimen through the cover slip, through the media into the lens. So hopefully you have understood what is magnification, what is the resolution, and what is the importance of the numerical aperture. Okay, so all the light which are falling on your specimen and then entering into your cover slip should enter into your lenses. The maximum light when it enters into the lenses, it is known as the numerical aperture, because it will give you a better resolution and a better image brightnesses.